In this video, we're going to look at the derivative rules for vector functions. So theorem 2.2.2, let k be a scalar, let c be a constant vector, let alpha of t be a scalar function. So we'll do an example in the next video to see what exactly that looks like if you're having trouble picturing that. And u and v be vector functions. Then the following derivative rules are valid. So we're going to prove one of them, we'll prove number 4, you'll do another one on one of your assignments, and then we'll take the others as given. So the derivative of a constant vector gives the 0 vector. If we have a constant multiple of a vector function, then we can pull out that constant k. If we have a scalar function times a vector function, then we have a product rule of the scalar. So we've got the derivative of the scalar times the vector plus the scalar times the derivative of the vector function. If we have the dot product of two vector functions, then we have another product rule. We have the derivative of the first vector function dotted with the second, and the first vector function dotted with the derivative of the second. We're going to prove that in just 1 second. Let's read through the other two rules that we have here in our list. If we've got vectors in R3, then we are able to cross them, and the same kind of product rule applies, but now we're taking cross products. So the derivative of the first crossed the second plus the first crossed with the derivative of the second vector function. And lastly, if we have a chain rule, if we've got a scalar function inside a vector function, well then the chain rule, as you might expect, it applies. Now this is a bit of notation you might not have seen before. This vertical bar means evaluated at, so the derivative of the vector function evaluated at the scalar times the derivative of the scalar. Another way of saying this using prime notation is u prime of alpha of t times alpha prime of t. So let's go and prove the dot product property. We'll do it for notation simplicity in the case that we've got vectors in R3, but other dimensions follow a very similar kind of proof. So let's let u of t have component functions u1 of t, u2 of t, and u3 of t, and v of t have component functions v1 of t, v2, nope, not a vector, v2 of t, and v3, no, I did it again, v3 of t. We want to examine the left-hand side here, so let's use the prime notation. I think it's maybe a little lighter for notation, so v of t dotted with u of t primed. Well, that's going to be the derivative of the dot product, so u1 v1, or I guess I've written the v's first, so let's do that, v1 u1 plus v2 u2 plus v3 u3 primed. We can distribute the prime onto each of those. These are functions, remember, v2, u2, those are functions of t, which means that when I go any further, I need to use product rule. So v1 prime u1 plus v1 u1 prime, v2 prime u2 plus v2 u2 prime. And the same thing with the last, v3 prime u3 plus u3 v3 prime. So now if we go and collect together those terms that have primes, oh, I just wrote the same thing twice there, didn't I? That's not good. So that should have been v3 u3 prime. So if we collect together the terms that have the v's primed, so I've got v1 primed, v2 primed, and v3 primed, dotted with u1, u2, u3. And if we look at the terms that have the u's primed, So this is plus v1, v2, v3 dotted with u1 prime, u2 prime, u3 prime, which is exactly what we were asked to show, v prime of t dotted with u of t plus v of t dotted with u prime of t. So in the next video, we'll do a couple of examples where we apply these derivative rules.